Target audience in this video is calculus students who have had to learn the difference quotient in an algebra class or maybe a pre-algebra class before, but they don't remember what it is because it was probably really boring and you didn't get to see why it was cool. Well, the reason why it's cool actually lies in calculus. But it's been so long that you might have forgotten what the difference quotient is. So this is going to be quick and very pausable. Please pause anytime I'm talking too fast. If you're following along, please write these three down and leave lots of space. We'll be working through all three. Let's evaluate each of these functions at x plus h. Let's get the dirty work out of the way in the beginning. This is usually where students feel the ickiest about it, so we're going to knock that out. If you can do this on your own, pause here. We're going to replace each x with the quantity x plus h, and then we're going to expand the binomials. Let's talk about expanding the binomials. This is going to be a shortcut to multiplying a bunch of binomials together, and we have patterns for them. So on the left side, the x plus h, that quantity raised to the first power, to the second power, and to the third power, you're going to see those a whole lot. You should probably commit those to memory. But then also, these are all connected to what we learned a long time ago, maybe in a pre-calculus class, maybe in an algebra class, to Pascal's triangle. Note the connection. Here's that first function. It's linear. It's not too bad. Did you get to the same f of x plus h? That's on screen. Evaluating g of x plus h in that quadratic. And now for the cubic function, evaluating k of x plus h. We already have the f of x plus h to copy over. I'm going to subtract the f of x, divide everything by h. I'm going to simplify, combine like terms. And notice, now when I simplify, I just get a plain number, no variables, just a constant. That is curious. Now that quadratic function, we have our g of x plus h to substitute in. We have our g of x. We're going to distribute that negative. And something you might notice is that everything in that minus g of x has some sort of mate to cancel with. So that negative 2x squared has a positive 2x squared that came from the g of x plus h. Then plus 3x has a minus 3x to cancel with. That minus 7 has a plus 7 to cancel with. Everything that we subtract from the g of x has some sort of mate from the g of x plus h to cancel with. And so therefore, you'll see this pattern over and over again. After you combine like terms, every single term that you have left over in your numerator will have an h in it. If it didn't have an h, then it had something that's subtracting it out. And since every single term has an h, I can divide each of my terms individually by h. Now they're going to get spicier pretty soon here, but right now we're sticking with polynomials. So what I would do right here is I would look for everything that came out of minus k of x, and I would find its mate to cancel with, so that when I combine like terms, I have a lot fewer things to work with. But I would start with that minus k of x stuff. Use that as a guide. All right. After you simplify those fractions, and by that I mean divide each of those terms in the numerator by h, did you get the same difference quotient as me? So why are we doing all this work? Take a function, any function. I'm picking the quadratic function that we've already discussed. So here's a function, and we want to find the tangent line that just goes through that function at one point. Let's call that one point x, f of x. But I can't find the slope at one point, I need to. So we're going to introduce a second point. The idea is that this point, the one that we're introducing right here, there is some sort of horizontal space between these two, and the horizontal space between these 2 points is h. So if this is x over, and then we put another h with it, this must be x plus h over, and then it's f of whatever that was, so f of x plus h. Now, as soon as we do that, let's find the slope of the secant line. And we know that the slope is y2 minus y1 over x2 minus x1. That simplifies a little bit, and lo and behold, the slope was the difference quotient. And this is where we get to transition from algebra to calculus, because I can't say that h is a 0, because it would create an undefined in a fraction, and that's like swearing in math, you can't do that. But we're going to say the limit as h gets really, really close to 0, or it's a scooch. Calculus right here, the calculus is going to scooch this h closer and closer and closer until there's virtually no space between them, and then we make a pretty good educated guess and say, well, looks like it's right about there. And then we can find the slope kind of sort of using 1 point. And that is why calculus is beautiful. That's at least why we have to slap a limit on a difference quotient. Now, concerning that the difference quotient was really a slope the whole time, remember that very first function? It was linear. So if I try to give it this extra h, it doesn't really matter what that is, because it's going to be the same slope the whole time. That's why the difference quotient on something linear was just whatever the slope was to begin with. In this case, 4. Now, we already did this one, but notice how when you start applying those limit laws, then that h term becomes 0 and it's gone. So you just have that 4x minus 3 left over. And here's that cubic function with the obligatory secant line as it travels around. But as we start scooching that h closer and closer, all of a sudden, they behave as 1. And then you get that tangent line. And then the limit as h approaches 0 gives us a polynomial that's much easier to work with. Isn't it lovely?